Hello, my name is Tushar Singh, and in this video we are going to discuss the first internal test paper of algorithm design and analysis. Let's get started. Question number 1. Complete the table after simplification of the corresponding recurrence relation. A table is given here which has the following columns: algorithm, relation, time complexity, space complexity, and power complexity. The given algorithms are linear search, binary search, factorial, tower of Hanoi, binary tree traversal, merge sort, quick sort, Strassens matrix multiplication, Karat-Suva, integer multiplication. And here are the recurrence relation given for the same. And we have to find all of their time complexity, space complexity, and power complexity. But first let us understand what is time complexity, space complexity, and power complexity. Time complexity may depend on various factors such as the specific input of the algorithm, the efficiency of the implementation, and the use of any auxiliary data structure or algorithms. In practice, the actual running time of an algorithm may also be affected by various external factors such as hardware limitations, operating system overhead, and the size of the input data. And the time complexity of linear search is O(n), binary search is O log n, factorial is O(n), tower of Hanoi O 2 to the power n, which is exponential, binary tree traversal O(n), merge sort O(n) log n, quick sort best case n log n, quick sort worst case n square, Strassens matrix multiplication n power log base to 7, Karat-Suva integer multiplication n log base to 3. What is space complexity? Space complexity may also depend on other factors such as their implementation details and their specific inputs to the algorithm. In some cases, the specific complexity may also be affected by the use of auxiliary data structures or temporary variables. Space complexity of linear search is constant, binary search constant, factorial constant, tower of Hanoi big O of n, binary tree traversal big O of h, where h is the height of the tree, merge sort O(n), quick sort best case O log n, quick sort worst case O(n), Strassens matrix multiplication O(n) square, Karat-Suva integer multiplication O(n) log base to 3. What is power complexity? The power complexity of an algorithm is a measure of how the algorithm running time grows as the input size increases. It is typically expressed in terms of exponent in the running time big O notation. Note that the power complexity of the algorithm are not same as their time or space complexities. These time and space complexity may have different constant or lower order terms that affect the actual running time or memory usage of the algorithm. Power complexity of linear search is n, binary search is log n, factorial n, tower of Hanoi exponential, binary tree traversal n, merge sort n log n, quick sort best case n log n, quick sort worst case n square, Strassens matrix multiplication n power 2.81, Karat-Suva integer multiplication log base to 3. Let's see the derivation of linear search. The recurrence relation for the linear search algorithm is Tn equal to Tn minus 1 plus big O of C, where C is a constant, where n is the size of the input. To solve this recurrence relation, we can use the recurrence tree method. The recurrence tree relation can be written as following, as you can see here. Therefore, the time complexity is O(n), space complexity is O1, and linear search power complexity is O(n), which means that the running time of the algorithm grows linearly with the size of the input. Binary search Tn equal to Tn by 2 plus OC, which gives us the time complexity and space complexity of binary search. We can use Master's theorem to find the time complexity, which will be O log n, and the space complexity is O1 and the power complexity is log n, which means that the running time of the algorithm grows logarithmically with the size of the input data. The recurrence relation for the factorial function is Tn equal to Tn minus 1 plus OC, where n is the input of the factorial function. To solve this recurrence relation, we can use the recursive tree method, which will give us the time complexity big O of n. The time space complexity will be O(n) because the function calls itself recursively n time, and each call creates a new stack frame on the call stack, and the power complexity of the recursive function is O(n). The recurrence relation for tower of Hanoi problem is Tn equal to 2Tn minus 1 plus OC, where n is the number of disk moved and C is the constant time taken to perform a disk move. We can solve this by recurrence tree method, which will give us an exponential time complexity, and the space complexity is O(n) because the function calls itself recursively n times. The power complexity of tower of Hanoi algorithm is 2 to the power n, which is exponential, which means that the running time of the algorithm grows exponentially with the size of input data. The recurrence relation for binary tree traversal in order, pre-order, or post-order is Tn equal to 2Tn by 2 plus O1, where O1 is the constant time taken to process a node and n is number of node in binary tree. We can solve this equation by Master's theorem, which will give us the result n log n time complexity and space complexity OH, where h is the height of the tree, and the power complexity of log n. Recurrence relation for merge sort is Tn equal to 2Tn by 2 plus On, where n is the number of element to be stored and On is the time taken to merge two sorted array of size n by 2. We can use Master's theorem to solve it, and the time complexity will be n log n. The space complexity of merge sort is On because the algorithm needs to create temporary array to store the elements being merged during the merge phase of the algorithm. The power complexity of merge sort is n power log n equal to n log n because the algorithm needs to perform n log n comparison and swaps in the first case. Quicksort best case and average case time complexity are same, which is n log n, and has a recurrence relation Tn equal to 2Tn by 2 plus On, which can be solved using Master's theorem. And the space complexity of quicksort is O log n due to the recursive call, and the power complexity is n log n because the algorithm needs to perform n log n comparison and swap in the best case. And the worst case recurrence relation is Tn equal to Tn equal to Tn minus 1 plus On square, where On square is the time taken to partition the array into two parts. To solve this recurrence relation, we can use iterative method. Therefore, the time complexity of quicksort in worst case is On square. Space complexity is On due to the recursive call since the depth of the recursion tree is n, and power complexity of quicksort in worst case is n cube since the algorithm needs to perform n square comparison and swap, and the recursion tree has depth n. Since matrix multiplication requires 7 multiplication, and the recurrence relation for it is Tn equal to 7Tn by 2 plus On star n, which can be solved by using Master's theorem and will give us a time complexity of n 2.81. Space complexity will also be same since the algorithm uses the recursive approach that requires the creation of new matrices, and the power complexity of since matrix multiplication is 2 On power 2.81 scalar multiplication at each level of recursion tree, and the depth is log n, which will give us O n 2.81 log n as the power complexity. Caret sub integer multiplication is used to multiply larger integers, and the recurrence relation for it will be Tn equal to 3Tn by 2 plus On square, which can be solved using Master's theorem. And the space complexity of caret sub integer multiplication is n log base 2 3, which is same as the time complexity since the algorithm uses recursive approach that requires the creation of new integers. And the power complexity of caret sub integer multiplication is On power log base 2 3 log n. Here is the final table. You can pause the video and see all the values. Second question, write recursive algorithm for polynomial representation. Here we are given how a polynomial representation looks in mathematics, and we have to write a program to represent it in our computer. So following steps need to be followed. Define a polynomial class that represents a polynomial. The class should have two attributes, a list of coefficient and an exponent for the polynomial. Second, create a recursive function called polynomial representation that takes a list of coefficient as input and returns polynomial object. Third, inside the polynomial representation function, check the base case. If the list of coefficient has only one element, create a polynomial object with the coefficient as only element in the list and exponent 0. If the list of coefficient has more than one element, remove the last coefficient from the list and create a polynomial object with the coefficient as the leading terms. Then the recursive call the polynomial representation function on the remaining coefficient and increment the exponent by 1. Multiply the returned polynomial object from the recursive call by x, that is multiply the coefficient of each term by x raised to the current exponent. Sixth, add the leading term polynomial object to the result of multiplication and return the final polynomial object. Here is the pseudocode for same. You can pause the video and see it. Third question, write iterative version of Tower of Hanoi problem. The implementation uses a stack to keep track of the recursive call that would be made in the recursive version of the stack. It starts with the initial call to move n disk from a rod to the to rod using the aux rod as an intermediary. In each iteration of the loop, the top call is popped from the stack and executed. If there is only one disk to move, it is moved and the loop continues. Otherwise, two recursive calls are pushed onto the stack, one to move n-1 disk from rod to aux rod using the rod as intermediary, and another to move n-1 disk from aux rod to rod using from rod as intermediary. Finally, call to move the remaining stack from rod to rod is also pushed onto the stack. This process continues until the stack is empty, at which point all necessary moves has been made to solve the Tower of Hanoi problem. Here is the pseudocode for the same. You can pause the video and see it. Thank you. That's all for this video.